Welcome to the video lecture series on principles of compiler design. In today's video lecture, we'll be learning about a most prominent topic called as type checking. So, type checking is part of compiler design. Type checking actually takes exactly in the phase of semantic analysis. So, we will be learning about this type checking along with the different types of type checking and the way how semantic rules are applied on the respective productions of type expressions. Uh, Now, this is Dr.K.N.Sivabalan. So, now the first we will learn about what is the role of a type checker. So, type checker is a part of semantic analysis which performs type checking tasks. The tasks are in general defining the range of the variables, converting one data type to another data type, and we can also see that an index variable can be only used in arrays. So, these are the limitations in the respective programming languages, and these limitations are actually checked by a type checking module. And as far as type checking is concerned, it is broadly classified into two types. One is called a static type checking, where it is done in the compile time, and another is dynamic type checking. It is actually done in runtime. So, when we type the program itself, these respective types are checked. Then the data types are checked, then it is called as compile time. So, while we run the program and the type checking is done, then that is called as runtime. So, there are specific languages which actually support static type checking. One typical example for static type checking is called as C programming. And this is a symbolic representation of a type checker. Pictorial representation has been given here. So, type checker actually stands between parser and intermediate code. Now, it takes an input called as syntax tree. Type checker generally takes an input called as syntax tree, and it will actually add certain additional information to syntax tree, and the outcome of the type checker is called as annotated syntax tree. It is called as annotated syntax tree, and this annotated syntax tree is actually given as an input for intermediate code generation, and finally intermediate code generation will be giving as an output. Now, we will be learning about in type checking in an elaborate fashion with the typical examples also. Now, when we talk about type conversion is also called as typecasting. In general, when we try to convert one data type to another data type, it is called as type conversion. So, say for example, we want to convert an integer data to a float data, or we want to convert a string data to an integer data. So, this type of conversions are called as typecasting. And there are two types of type conversions. One is called as implicit type conversion, another is explicit type conversion. And implicit type conversion, if one type of data is actually converted to another data type by compiler automatically, then it is called as implicit type conversion. For instance, if you have a lower data type and if you want to convert that into a higher data type, then we can do that without any data loss. So, this type of conversion is called as implicit type conversion. A classic example for this is, you know that byte is actually can occupy only 8 bits of data, and integer can hold 32 bits of data. And when compared to integer, byte is actually small in data size. So, here I try to convert a byte variable. A byte variable is converted to an integer variable. So, automatically when we assign b to I, automatically that will be getting converted to integer. So, in this case, and byte is converted to integer, so this type of conversion is called as implicit type conversion. So, there is no need to explicitly specify the data type while converting it, and automatically it will be converted to integer without any data loss. So, the reason for this is byte actually occupies only a small data amount. So, we can say that it occupies only 8 bits here. It can occupy only 8 bits, but when we when we say about integer, it is actually 32 bit in data size. Okay. So 8-bit can be easily accommodated in 32-bit. So this is called as implicit type conversion. In other sense, it is called as broadening of the data. Or the next is called as explicit type conversion. So if you are converting one data type to another data type by using some predefined functions, then it is called as explicit type conversion. Generally, higher data types will be converted to lower data types, but there is a compromise in data loss. So in this case, a small chunk of data will be lost when we try to convert a higher data type to a lower data type. So we just do it in vice versa. Now we want to convert an integer data to a byte data. Integer is actually 32-bit size. Here it is 32-bit size. It is 32. And when we talk about byte, it is actually 8-bit. Now when we actually try to convert that to byte with the help of this predefined function byte, so automatically it will be converted, but it will be converted with data loss. So this concept is called as explicit type conversion. So now we'll go for type checking with the rules which is provided here. The rules are given here in the form of protections, and the corresponding semantic actions is actually given on the right side. So when we talk about first protection rule, the first protection rule, E tends to E1 plus E2. Now if we say that E1 and E2 are identical data types, and if E1 dot type is equal to integer, then obviously the resulting type of E will be integer. That is the meaning of it. So if E1 and E2 are integer, then E will also be integer. Now when we come to the second protection, we are making a comparison here. I am using double equal to E1 is compared with E2, and we have to determine the output of this E expression. So if E1 and E2 are same data type, and if E1 is actually integer or boolean, so the resulting data type is always boolean here. It is called as boolean. So in this case it is boolean. Now if E1 is and E2 are integer or boolean, the resulting data type is also boolean. So that is the meaning of it. And when we come to the third one, E1 tends to inside the flanked by brackets, it is E1. So E1 E dot type is equal to automatically E1 dot type. The fourth expression, E1 tends to number. So number is an integer, so E dot type is also integer. Now when expression E is equal to true, so obviously E data type is actually boolean, and when expression E is equal to false, E data type is also boolean in this case. So these are the typical protections which is given and the respective semantic actions. Now we will apply these semantic actions in the corresponding problem. Now the problem is given as find the type of the expression where I have to evaluate 3 plus 4 and I have to compare with 8. So final result, we want to evaluate the type of this expression. Now as we will apply this grammatical rules here, protections here. So first I apply E tends to E1 double equal to E2. Then E1 is abbreviated into E1 in flanked by brackets. Then this E1 is abbreviated as E1 plus E2, and E1 is given as number which is equivalent to 3, and E2 is given as number which is equal to 4, and this E2 which is given to a number called as 8. So altogether we have 3 operands, 3, 4 and 8. So it has been drawn in a tree. So first we will evaluate from the bottom onwards. So we will take up the first tree here. The first tree is E1 tends to number. Now we have to evaluate this tree. Since E1 tends to number, number is 3. 3 is an integer, so automatically this E1 dot type should also be integer. So E1 dot type is integer. Next we will go for the next subtree on the right side. So right side E2 tends to number equal to 4. Since number is equal to 4, E2 type will also be integer. So E2 type is also integer. Now we go and evaluate on the right side now. Now E2 is equal to number equal to 8. Okay. Now since number is equal to 8, now E2 will also be belonging to type called as integer. So E2 dot type is equal to integer. Now we will evaluate this tree now. So this portion of the tree, E1 tends to E1 dot type plus E2 dot type. Now it is equivalent to synonymous to the production called as E1 tends to E1 plus E2. Now when these two types are integer, so automatically EDA type will also be integer. So based on the semantic rule. Now we will evaluate the topmost tree now, next topmost tree. So this tree will be evaluated E1 tends to inside the brackets. Now since this tends to a protection called as E tends to is flanked by E1. Now the result of this entire expression will be integer. So this expression will also be integer. Okay. Now we have to evaluate the topmost tree now, topmost node. It is E tends to E1 equal to E2. So now this tree has to get evaluated. Since we already know in the semantic rule, it says that when E1 type is integer or boolean or E2 type is integer or boolean, the final result is always boolean. So the final result is boolean. Okay. So this is the way of evaluating an expression, and you know that the meaning of this expression is, there is a meaning in this expression, and the type of the entire expression is called as boolean. Okay. So that's about type checking. Thanks for watching the video. Have a good day.